Hello everyone. Till now we have been looking at the CMOS logic family in detail. We saw how the combination and sequential circuits are made using CMOS. CMOS remains till date the most popular choice for constructing digital and analog for combination and sequential circuits. But there are few logic families, there are few design styles which are popular for specific applications. We look at a couple of design styles. We call them circuit families. So CMOS is one circuit family. What we looked at was static CMOS. Static means if I go back and look at the schematic of an inverter. Static means that the output is either driven by VDD or driven by ground at all times, except when the input is switching. Only for a fraction of time it is transitioning. Otherwise, at all times the output is driven either by VDD or ground. That is why we call it static. So we were looking at CMOS, and specifically we were looking at static CMOS. So now we look at a couple of logic families. One, we look at pseudo NMOS logic. We'll first look at why do we want to go for anything else? What are the reasons? Why are we compelled to look out for other logic families? We look at dynamic logic. Again, dynamic logic is a variation of CMOS only. It is a static. We had static CMOS. Now we have dynamic logic. In fact, we saw one of the logic families earlier. We saw pass transistor logic family in earlier lectures, and we saw the advantages and disadvantages. The advantages being low area. The disadvantage, a very big disadvantage of pass transistor was the VT drop, and in fact we even saw how to solve the VT drop. So we constructed a transmission gate out of it, connecting PMOS and NMOS together. So we have been seeing variations of CMOS, but in this lecture we see in detail these two logic families. Now, what makes a circuit fast? Since there can be three parameters of comparing different logic families. One obviously is the area, what is the transistor count. Second is how fast or how slow the cell is. Obviously we want faster. And third is what is the power consumption. In earlier technologies or smaller chips, power consumption was not a big issue, but power consumption is in fact one of the most important factors now. Even more so when we consider that a lot of devices that we use are battery powered. So obviously we want something very economical in terms of power. So here what we are looking at, the angle we are looking at is purely the timing. We are not looking at we are looking at area and timing. We are not talking in terms of power now. So the question is, what makes a circuit fast? How fast or how slow a circuit is depends on the current. How fast does the current charge or discharge the capacitor? So I is equal to C dV by dt. So the propagation delay is proportional to C by I delta V or dV by dt. Low capacitance makes a circuit faster because the smaller capacitance takes less time to charge and discharge. High current, we talked about that, and a small swing. A small swing means, let's say you want the VDD supply, let's say is 5 volts, and you want a small, and the time it takes for the output to charge from 0 to 1 or 1 to 0. Let's say that the time is something, but if I reduce the swing to let's say 2 volts, if I make VDD 2 volts, obviously going from 0 to 1 or 1 to 0 from 2 to 0 volts will be comparatively faster when compared to 5 volts. Logical effort is again proportional to Ci. We say that okay, I is equal to so the propagation delay is proportional to C by I delta V. Logical effort itself is also proportional to C by I. So if you notice the NOR gate on the right hand side here, this NOR gate. Now this is the way NOR gate is sized typically when I compare to a unit inverter. So now a NOR gate we see, let's see the input capacitance. So A will see the capacitance of 4C plus 1C, total 5C. Now majority of the input capacitance, or in fact even output C is 4C plus 1C plus 1C is 6C. The majority of the input capacitance and the output capacitance comes purely from PMOS. NMOS is a lesser factor here. That is why we are saying that PMOS is the enemy, because compared to NMOS, it has high capacitance for a given current. Now this is what makes people ask that what if I take PMOS out of the equation? If I want to take PMOS out capacitance of the input or of the output, whatever. So one of the most famous circuit families that tries to do that is called pseudo NMOS. So the CMOS it was a complementary MOS which has PMOS and NMOS connected together. Pseudo NMOS on the other hand has PMOS which is always on. So in older technologies, the NMOS processes had no PMOS. So what was used was a pull-up transistor that is always on. So this is the variation over CMOS, that the pull-up network is always on. Now the pull-down network can be on or can be off based on the value of the input. So let's see how this circuit works. So again, this is an inverter. So when Vin is 0, NMOS is off, this NMOS is off, this NMOS is off, PMOS is on, and Vout is 1. So not different in a regular inverter. The difference comes when Vin rises. When Vin becomes 1, the NMOS is on now, but PMOS is pulling Vout to 1. Now, if NMOS is very comparatively stronger than PMOS in terms of current carrying capability, then Vout will go to 0. Now the time on the logic level, the time after which Vout goes to 0 here depends on the relative strength of NMOS with respect to PMOS. That's why we say that there's a ratio issue. How do we size a transistor? So this is a graph. Now in this circuit, the width of PMOS is given to be P, and we have made NMOS to be 16. Now this is an inverter characteristic Vout versus Vin, and the voltage characteristics are plotted for 3 different values: P is equal to 4, P is equal to 14, and P is equal to 24. Now as we go here, we see that this gate is becoming more and more skewed. What do we want? We want the characteristic to be as close to the unit CMOS inverter, which is this one, this side. So the rule of thumb is that we make PMOS 1/4 effective strength of the pull down network. Now in a typical unit inverter, usually NMOS is 1, if NMOS is X, PMOS is 2X. Now we are saying that we make PMOS 1/4 compared to NMOS. So if NMOS is X, the PMOS will go X/4. Earlier it was 2X, now it goes X/4. Let's see the circuits. So this is a typical structure of a pseudo NMOS. You have a pull down network implementing function F. Your pull up network is almost non-existent. The pull up network is only a PMOS which is always on. So the logic function is only implemented by the NMOS, which is the pull down network. What do we strive for in this case? We strive for unit current on output to compare with the unit inverter. So these are the circuits: inverter, NAND, and NOR. If you try to see the similarity with the CMOS, you would see that the pull down network remains same. The pull up network is replaced by a PMOS which is always on. That's the only difference. Now how do we size them? So we put some numbers here. So if we talk about this inverter, we say that okay, we first fix NMOS. We say NMOS is 4/3. So by the rule of thumb, the PMOS should be 1 by 4 of this size. So earlier it would have been 8. Now it's 2 by 3. So earlier, and without this being a pseudo NMOS, let's say if it were a PMOS, the PMOS would have been 8 by 2. Now I'm multiplying that by 1 by 4, that being the rule of thumb. So 8 by 3 into 1 by 4 becomes 2 by 3. So this is how we size this inverter. NAND 2, NOR 2, again you could compare with the unit inverter here. So NAND 2 to make the pull down, so the pull up network now will remain same. For NAND and NOR, the pull up in fact remains 2 by 3. What we are worried about is the pull down network. So going to NAND 2, we see that A and B are in series. So the resistance will increase. So what we do is we double the width of each of the transistors. So it becomes from 4 by 3, it becomes 8 by 3, 8 by 3. For NOR 2, we see that they are in parallel, so they remain 4 by 3 because assuming only one is on at one time, so it remains 4 by 3, same as inverter. Now let's see what happens to the values of G and P. Going back to the last lecture, G represents the logical effort, which is by definition it is the capacitance seen by the input of a gate divided by the capacitance at the input of an inverter, a unit inverter. So we saw that an inverter is the G value is 1. P is the parasitic capacitance, which is again the value of the capacitance seen at the output of the gate compared to the value of the capacitance at the output of an inverter. So now in this case, whenever I'll fill in the values and I'll explain how they are derived. Now in the inverter, this inverter, the pseudo NMOS inverter, is same as the regular CMOS inverter. In the case A is 0, that is NMOS is off. So in CMOS inverter also PMOS is on. In this inverter also PMOS is on. So the case of Y being pull up, that is GU means G in the case of pull up, and GD means G for the case where it's a pull down. Now, now GU and PU, that is the cases where it's pull up, are exactly same like CMOS. So it should be very easy to calculate the value of G and P. Here A sees this divided by 3 is nothing but we are saying that the length remains 3. So what we are comparing it against is a unit inverter for which again the length remains 3. So in fact PMOS and NMOS were sized as 1 by 3 and 2 by 3. Here it becomes 4 by 3 and 2 by 3. So for the GU, so A sees the input cap to be 4 by 3. So GU remains 4 by 3. So 4 by 3 divided by 1 of the inverter. The GU remains 4 by 3. PU, so Y will see the cap of PMOS on and NMOS 4 by 3. So it's 2 by 3 plus 4 by 3 is 6 by 3. Now let's consider the pull down case. Now what happens during pull down is what makes it different from a regular CMOS inverter. For the case of pull down, the PMOS and NMOS are both on. Now in this case, the capacitance seen by both input and output are reduced. Now in the earlier inverter, in the CMOS inverter, A sees the cap of both NMOS and PMOS. But here A is just seeing the cap of NMOS. So now we say that so in both G and P cases, the capacitance gets further divided by 3. So whatever is the value of GU, GD will be the value of GU divided by 3. So 4 by 3 becomes 4 by 9. Similarly, PU 6 by 3 becomes 6 by 9. In fact, this is what our aim was. Our aim was to reduce the capacitance on output and input by replacing the pull-up network with an always on CMOS. The average value is simply GU. The average is simply GU plus GB divided by 2. P average again is PU plus PD divided by 2. Similarly, now for NAND you could do that. A and B both see 8 by 3, so GU becomes 8 by 3. GD becomes the value of GU divided by 3. Similarly, Y sees 2 plus 8 by 3, which is 10 by 3. PD becomes 10 by 3, again further divided by 3. You could also do this similar exercise for NOT. So we see that the value of GN, by the values of GNP, we see that the average value of GNP is lower when compared to a corresponding CMOS structure. In fact, the area is also lower. You notice that the whole pull-up network, let's say for an n input NAND gate, there will be n PMOS, but here there is only one PMOS. So then why is it not popular? That's the question, right? It has lower area, it has lower capacitance, so it would be faster than a regular CMOS, but then why is it not popular? The most pressing concern here is that pseudo NMOS draws power whenever Y is 0. Whenever Y is stable 0, NMOS is on, PMOS is also PMOS is always on. Y0 means one of the input is 1, one of the input values that NMOS is 1. So NMOS is conducting. So now there is a direct path. We will go back to the previous circuit, previous inverter. So whenever Y, whenever this node is 0, that means this node has a path from ground. This is the ground. So this node has a path from ground. Plus this is on, so there is a path from VDD to ground. With resistance offered by this PMOS, there is some resistance offered, and this NMOS there is some resistance offered. This NMOS. But otherwise there is a path that exists. Compare it with a CMOS, where there is almost no power consumption, almost no current, I mean very small leakage current, whenever Y is either 0 or either 1. But in this case, it is not so. In this case, it draws power whenever Y is 0. This is static power. P is equal to I VDD. And this, now consider a big chip or even a moderate size chip with thousands or millions of transistors. This can be a really big problem. That is why pseudo NMOS was never used. It might have been in use in some special circuits for a very specific case. Otherwise, at a general in the industry, pseudo NMOS is not used just because of this. So the special case, one special case can be, we can use pseudo NMOS sparingly for wide NORs. Now what is special about NOR? If you write down the truth table for NOR, you would realize that, let's say you have a 3-input NOR. The 3-input NOR will give 1 only for one condition, when all 3 inputs are 0. Otherwise it will be 0 most of the time. What it means is that the probability of a 3-input NOR going to 0 is 7 by 8, which is very high probability. So that means the output is 0 most of the time. But now we want to turn off PMOS when not in use. So the probability of Y being 0 in this case is very high. So Y being 0 is very high, and we exploit that probability and we connect an enable signal at PMOS, and so this enable signal, this PMOS would be disabled for majority of the time. What this does is, it gives us a NOR which is lower in area. Obviously we have an extra circuit for enable, but that is a very small design. So we have a NOR which is less in area and probably faster than a regular CMOS. So this is one special case where pseudo NMOS can be used. But for the limitation of this course, within the purview of this course, and when we use synthesis, we will not encounter any pseudo NMOS. All circuits used in standard cell library, all designs are CMOS or they have transmission gates. That is all. There is no pseudo NMOS. But it's good to know that to reduce area or to reduce transfer count or to make the circuit faster, what else can we do? Right. So this is one example. Now let's look at a second set of logic family, dynamic logic. It's a very interesting concept. It is just an extension of CMOS. It doesn't result into a decreased transfer count, so the area in fact increases a bit, but it is very fast in some cases, and it is in fact it is used in some special designs. Now let's compare the three logic families. The inverters are drawn here. So one is static, other is pseudo NMOS, third is dynamic. So the difference dynamic has over static is that pseudo NMOS, it was PMOS which was always on. Dynamic, there is a extra input. This extra input is called, let's call it top. Now a dynamic, so this PMOS will be on when clock is 0. We call this pre-charge mode. This PMOS would be off when clock is 1. We call it evaluate mode. Now what happens during these modes? Now pre-charge, as the name suggests, pre-charge means pre-charging the node to some value. So in this case we are talking about node 1. So what this clock input does is, whenever it is 0, Y is pre-charged to VDD. So there is a path from VDD to Y, and Y gets pre-charged. So this timing diagram here tells us that Y remains 1 whenever it is in pre-charge mode. Whenever this clock goes to 1, the PMOS becomes off, and now Y is ready to take on whatever A gives it. Right? So whenever if A is 0, now this NMOS is off, Y is 1 because it was pre-charged already. When A is 1, NMOS is on, Y is 0 because it connects to VDD now, it connects to ground now. But correspondingly, when you compare it with pseudo NMOS, there is no path from VDD to Y. So in this case also, just like CMOS, only one thing is on at one time. So during evaluate mode, let's say if A was 1, Y would go to 0. Again at pre-charge, Y would go to 1. Why is it dynamic? It is dynamic because Y holds the value. Let's say if A continued to be 0, NMOS would be off and Y would be holding 1 even during evaluate mode. It is not being charged. In fact, it is being discharged. It holds 1, but it is being discharged. So there is a dynamic charge there on Y. That is why it's called dynamic logic. And plus, we use a clocking signal to pre-charge and evaluate, which is again a dynamic signal. So you could say that the name even comes from there. Now let's look at a few interesting circuits. Okay, one question comes that what is pull down network? What if in the earlier slide pull down network is, let's say, A? What if A is during the pre-charge itself, A is 0, or let's say A is 1, that is NMOS is conducting. So if NMOS is conducting, then it is not a good scenario because Y is being driven by VDD and also by NMOS, which is a problem we saw with pseudo NMOS. We do not want that. So what do is we add a foot. We add a foot to A, which is again driven by a clock. So this clock. So whenever during pre-charge mode, this NMOS is off. This NMOS is off. So it prevents Y from getting. It prevents Y from getting driven by VDD and ground from it at the same time. So a typical domino logic would look like this. So you have a putted domino logic would look like this. You have put, you have inputs going to a pull down network F comprising wholly of NMOS, and you have a pre-charge transistor driven by a clock. Unputted, you just remove the put, but you still need the pre-charge transistor. Now, what happens to the logical effort? So, logical effort is a very good tool in comparing the capacitance of different type of logic families. So, we again use that. So, I'll fill in the values on the next page. So, inverter 1 and 1. So, A will always see an input value of 1, 1C. Compare this with an inverter which A sees the value of 3. So, G for this case, for G for domino logic becomes 1 by 3. Again, I'll repeat. A here sees the capacitance of 1C because of this NMOS. Because of this NMOS, it sees just 1C. A corresponding unit CMOS inverter sees value of 3C, 2C coming from the PMOS. So G for domino becomes 1 divided by 2. Similarly, P, this Y sees 1C plus 1C, which is 2C. Compare it with a unit inverter which has an output cap of 3C. So P for domino becomes 2 by 2. Let's compare, go to the footed case. Second, here A sees 2C, Y sees 1 plus 2, 3C. Divide by 3 in both the cases, compare with the unit inverter, so we get a value of 2 by 3 and 2 by 3. Again, for NAND 2, we can do the same exercise. Y sees 1C plus 2C, 3C. So P becomes 3 by 3. A sees 2, so G becomes 2 by 2. For footed case, GD becomes A sees 3, so G becomes 3 by 3. Y sees 3 plus 1, 4, so PD becomes 4 by 3. Similarly, you could do the same for NOR. Now we can see that obviously the footed one adds 2 transistors extra to the CMOS logic. The unfooted one adds 1 transistor extra. So dynamic logic or we call them also domino gates. We come to that. The dynamic logic in fact adds transistors to CMOS, so the area is more. The area is more, but on the other hand, the loading on A decreases. On inputs, the loading decreases. Why? Because input is only connected to NMOS network, it is not connected to the PMOS network. So the capacitance decreases on inputs, and correspondingly the circuit becomes fast. So what did dynamic logic do? Dynamic logic, in fact, used a similar concept as pseudo NMOS by realizing the logic function only by the pull down network. It does not use the PMOS pull up network. So in fact, sorry, I was wrong earlier in the sense that although dynamic logic adds extra PMOS and to the header in the footer, so 2 PMOS for the footed one, but it actually reduces transistor count for bit gate because the PMOS pull up network is not there. So it takes pseudo NMOS and adds some improvement over it. It adds the clock just to prevent the current leakage whenever output node is zero. Whenever output node is driven by the pull down network. So now let's see. So now there is one most interesting concept called monotonicity in case of dynamic gates. So dynamic gates require monotonically rising input during evaluation. What does it mean? Is that the input should go from 0 to 0, that is no transition, or 0 to 1, or it should remain at 1. It is not allowed for input to go from 1 to 0. And why is that? Now let's say, so during a pre-charge mode, Y will always be 1. Now let's say during evaluate mode, A was 1 during the pre-charge mode, and during evaluate mode, A went to 0. Now if A went to 0, then this is during evaluate mode, the pre-charge one, this is off and this is on. This is on, the put NMOS. So A goes to 0, Y cannot go to 1 now. Why? Because during evaluate mode there is no path. The path from VDD to Y does not exist. This path does not exist. So during evaluate there is no way Y can go to 1. So see, the job of charging Y to 1 is on the PMOS, which is driven by a clock. Now, if the CMOS is off, which in fact is the case during evaluate mode, nothing else, nothing else, no the logic that can take y to 1. So y will not become 1, and this is a problem. This is an invalid condition for this. Again, during y will only become 1 during the pre-charge mode. So output should have been should rise, but it does not rise during the evaluate mode. Now let's say if the evaluate mode is longer and you expect the output to rise, but it does not, so it's a problem. So that is why these gates are restricted. But on the other hand, a dynamic gate will produce a monotonically falling output during evaluation. What does this mean? This means, so see the case when I connect one inverter to another inverter forming buffer. So whenever A goes from 0 to 1, X goes from 1 to 0. But X going from 1 to 0 is not valid for the second, for this dynamic logic. So during pre-charge, both X and Y are 1. A, let's say, remains at 1. A remains at 1. So during evaluate mode, X goes to 0. But now X going from 1 to 0 violates the input condition for the second inverter. So Y will not rise, and this is a problem. So it's illegal for one dynamic gate to drive another dynamic gate. What should we do now? How do we construct circuits out of dynamic gates? The answer lies in domino gate. So what do we do in domino is that we follow a dynamic stage with an inverting static gate. So let's say this is I'll explain this circuit. This is a domino AND. So this part here is a dynamic NAND gate. The NMOS network here represents a NAND gate, and we add an inverter, a static CMOS inverter to it. So this becomes NAND plus an inverter becomes a AND, and this the union of this dynamic NAND and a static inverter is called a domino AND. So domino is simply a dynamic gate followed by a static CMOS inverter. This solves the problem of monotonicity for us. It produces monotonic output. So for the case where the let's say W node was falling, X now is rising because X is invert of W, and it doesn't pose a problem for the next gate. So for the next gate, still you have X which is rising, which is monotonically rising. Again Y falls, and Z is fine. And since Y to Z is a static CMOS inverter, it doesn't have any restriction. The logic works just fine. So we could also draw a logic diagram here representing this gate. So you have a dynamic NAND, then a static inverter, then again a dynamic NAND, and again a static inverter. So we convert this dynamic NAND to a domino AND. So this is a domino AND, an extra input being the clock side. Again, this is domino AND. Now let's see what domino optimization means. So each domino, why is it called a domino? Each domino gate triggers the next one, like a string of dominoes toppling over. That is why we call it a domino logic. So gates will evaluate sequentially. What it means is that let's say you have n number of gates connected sequentially. In fact, let's go to the previous one. So you had a domino AND driving again domino AND. So the nodes X and Z, or in fact not nodes X and Z, but nodes W, this node here, and the nodes W and Y will be pre-charged at the same time, because the same clock input goes to both of them. So now for this logic, there will be a pre-charge cycle which will pre-charge W and Y to EBD, and then there will be the evaluate cycle. But evaluate cycle happens sequentially. Why? Because W will get the effect of A or B after some time, and Y will get the effect of X after some time. So evaluate happens sequentially, but pre-charge happens in parallel. So evaluation obviously is more critical than pre-charge. So This is one example of a gate. You have this is an example of a footless domino. So this becomes S0, S0 and D0, S1 and D1, S2 and D2, S3 and D3, and you have an inverting. You have a static gate here. This is static gate which converts it into a domino model. So high skewed static stages can perform logic. What it means is that since evaluation is more critical than pre-charge, that means one logic level. So logic level 1 is not critical. It anyway gets to logic level 1 during pre-charge, but going to 0 is critical. So the gates have to be skewed. They have to perform better during one direction as compared to the other. Skew gate means that it will be faster for one case compared to the case. The two cases being the logic output going from 0 to 1 or 1 to 0. The skewed gate, let's say, will do a rise transition much faster than a low transition. So this is what it says is there, that high skewed static gate stages can perform logic using domino optimization. Now there is a very interesting concept called domino, dual rail domino. Usually domino only performs non-inverting function. Please remember, domino is dynamic plus one inverter. Dynamic gate performs simply like CMOS performs non-inverting function, but we add an inverter to it to make a domino logic, domino gate, and domino only performs non-inverting function. So how do we now? We need and, or, and not, the three basic gates we need. Now we don't have an inverter here, so what do? We make something called a dual rail domino. Now dual rail domino, the structure is like this. So this YH is an input, YI is YH is output, YI is invert of YH. So YH and YI, the outputs of dual rail domino, are complementary to each other. The inputs are also like that. So let's say F gets inputs, regular inputs, F bar gets complementary inputs. So dual rail domino, what it does is that it takes true and complementary inputs and correspondingly gives true and complementary outputs. So sig H and sig I are nothing but YH and YI. So whenever they YH and YI are 0, that means nodes here are 1. These nodes are 1. That means it is in pre-charge stage. So whenever pre-charge happens, these nodes, the nodes in blue, I have highlighted in blue, these nodes get pre-charged, and only in this case the outputs YI and YH are not complementary, but they are both 0. Otherwise, during all these stages, they are complementary and they will never become 1 and 1. Both. It is invalid, they will never become 1 and 1. Now let's see an example of a dual rail domino gate. So since they produce complementary outputs, let's see an example of AND and NAND. So the principle here is that you need, let's say you have a 2-input gate, so you need 2 regular inputs, A and B. So these are the 2 inputs, A and B, AH and BH. You also need the inverted of this, so you have A inverted and B inverted. AI is nothing but complement of AH. The function here, the function represented by AH and BH, will be complementary to function represented by AI and BI. So on one side you make an AND connection, other side you made a OR connection. Now let's see the one on the right hand side. So this is AH, regular inputs, I'll call them simply A and B. So A and B inverted. So this is A and, this is NAND function, A and B complement, because it's an NMOS pull down method. So A and B complement goes to an inverter, becomes A and B. On the other hand side, the pull down logic is A invert or B invert, A invert or B invert, it is A invert or B invert invert. So A invert or B invert invert becomes A invert into so it becomes, so the pull down network on the left hand side is A invert plus B invert and complete invert of that. So it becomes A into B using De Morgan's theorem. It goes to an inverter, becomes A into B bar. So it becomes a Dan function. So pull down networks are also conduction complement. The inputs are also complementary to each other. The outputs are also complementary to each other. Obviously, the area is big, but you get two outputs. But the number of inputs are also high. You have to also consider the availability of the inverted input. But then circuits are again designed for optimize, realizing the fact that you have two outputs available which are conduction complements, and you correspondingly optimize the design in such a way. This is a very interesting circuit of XOR and XNOR. Now what you could do is you could first draw a circuit just like AND and NAND. So AND, a two input AND needs for one function it needs two transistors in the pull down network. The other one also needs two. So you would assume that for XOR now, XOR is a very interesting again. So you see that it shares transistors. So A XOR B. So you have A, I'll just call AH A. It is ANDed with B invert and plus A invert ANDed with B. Complement of that, since it's a pull down network, we have to have complement of that. This node here is the complement of whatever we saw, that is A into B invert plus B into A invert. Complement of that, it goes to an inverter, gives the draw function. Similarly, the node here gives the XOR function. You could try drawing it on paper and see that how the transistors are shared. By sharing, I mean that there are connections from in the previous circuit. There is no sharing of nodes between the left hand between this part and this part. There is no sharing of nodes. It's just that the one on the right hand side represents and the one on the left hand side gives NAND. There is no sharing. But in the case of XOR and XNOR, there is sharing in the sense that the node here is shared to this circuit, and the node here is shared with this circuit. Now, let's look at what are the limitations or the advantages. We look at both the sides for dynamic logic. Now, a dynamic node, as I mentioned before, a dynamic node floats high during evaluation. Let's say for an inverter, the input is 0, the output is 1 during evaluate phase, but that output is a hanging one. That means it is not driven by VDD. So over time, it will lose its value. The transistors are leaking. The off current is not exactly 0. So during a long evaluate time, let's say the node stays at 1, it will start losing it will start degrading from VDD. It will leak over time. This time was formerly milliseconds, now nanoseconds. It will go off in nanoseconds. It won't retain the value. So now we use a keeper. Keeper is nothing but we need a weak PMOS so that it doesn't fight evaluation. So now please note that we need a keeper only for the case where Y is 1. So Y means or sorry, in this case the node is X. So whenever X is 1, we need to keep charging it. So whenever X is 1, what does it mean? So it's an evaluate phase. So this is off. I'll cut this off. This part is off. X gets X. The value on X being 1 tells us that it was 1. It was pre-charged, and now this part is also off. A is 0. So now X is kind of a hanging one. So we need to pre-charge X. We need to keep feeding X to VDD. And how do we do that? We invert X, if the inverter is already there. We invert this and give the output to a PMOS connected to VDD. Now X is 1, Y is 0, this PMOS is on. So now it keeps charging X. In this case, X is not floating and it keeps on charging to VDD for the complete evaluate phase. So we are fine, it will not leak. So this is one problem we have to solve in domino orbit or dynamic gates. Other problem is charge sharing. Now let's look at this case. This is a dynamic NAND. Now in dynamic NAND, let's say B is 0, one input is 0. Now A goes to 1 from 0. Now if A goes to 1, ideally the value on Y should not change. A NAND Y here, since B is 0, it is not connected to ground. Y was, let's say, already 1, it was pre-charged to 1. Now the value on Y should not change because B still is 0. But what happens? This here conducts. This NMOS here conducts, and now we could say that X and Y are similar nodes. So the capacitance of X will now affect the node Y, and the value on Vx will be equal to Vy because this is conducting. Vx is equal to Vy now will become Cy upon Cx plus Cy into Vd because there is some voltage drop. So the value on Y is not in fact VDD, it is lower than VDD. How much lower? Depends on the capacitance Cx. Now when would this problem not occur? This problem will not occur in two cases. Case 1, if we are able to make Cx 0, or case 2, when Cy is much greater than Cx. How do we do that? To make Cx 0, what we do is we charge the node, we also pre-charge node X. In fact, we typically need to pre-charge every such node. If you had like a 3 deep down logic, we have to pre-charge even that intermediate node. So all intermediate nodes have to be pre-charged to prevent this effect. What pre-charging means? Pre-charging means actually making Cx 0. Other thing I talked about was making Cy big, but then Cy will be big only when the load is higher. So big load capacitance Cy also helps, but again this is a disadvantage that a big load obviously will take a lot of time to charge up or charge down. So again it will be a slower system. So so we saw one problem of leakage. We saw a problem of leakage. How to solve it? We saw that we need to add a keeper. So see, now we are modifying a dynamic circuit to reduce or to remove the incompetency it has when compared to CMOS, regular static CMOS, and in turn we are actually adding logic. So here we added a PMOS. Again we added a PMOS to kind of recharge it. So the advantage, the area advantage it has over regular CMOS is kind of decreasing now. Even when you, more specifically so when you consider small gates, when you consider gates like 2 input NAND, 2 input NOR, majority of the gates are 2 or 3 inputs. Now in case of 2 or 3 inputs, the area advantage offered by a dynamic logic or a domino gate is not much. Right? Such circuit might be even bigger than the corresponding static CMOS. Other problem is, the third problem is the noise sensitivity. The dynamic gates are very sensitive to noise. Why? Because the input high value VIH is equal to V2. It means that the NMOS here. Now let's go back. Let's go back to the inverter circuit. So now let's see this dynamic inverter. Now let's say the input on A is 0, NMOS is not conducting, so Y is fine. But now let's say there's a bump on it, there's a noise on it. So A was 0, and now there's a slight bump, slight noise on it, and A goes low again. This is what we call noise. That is unwanted value changes, unwanted voltage level changes on inputs. It's called noise. Now what happens to NMOS here? Let's say the phase is evaluate. It is not a P-charge. It is an evaluate phase. Now this NMOS starts conducting for this time, for this amount of time whenever there is a noise on A, and only if the noise on A is such that the level exceeds the threshold voltage of NMOS. So this input here is more than Vt of NMOS. Now Y will start feeling the effect of this. This does not happen in an inverter. You see that in a static CMOS inverter, the noise margins are very high. It's a very robust circuit. It does not happen there because you have both NMOS and PMOS. Right? Now Y has the effect of A even when there is a noise of A on A which is as small as Vt. Now let's fill in some values. So VDD 5 volts. A Vt let's say would be typically 0.6 to 0.7 volts. So if the output is getting affected even when input is, let's say 10%, even 10% of VDD, 10 to 15% of VDD, the noise margin is very low. That is why we say that the dynamic gates have a low noise margin, and this is one major disadvantage which prevents a more wide use of these. So they're very sensitive to noise. Again, outputs. So we saw that outputs are floating in some cases. Let's say if we do not have a feedback PMOS, we don't have a keeper PMOS. In that case, output is floating, and a floating output is more susceptible to noise. A regular output driven by either VDD or ground is actually a very good, very robust point, very robust mode. It won't see much noise effect. But a floating output, any small noise can affect its value. What are the noise sources? Noise sources are capacitive crosstalk. This capacitive crosstalk is a very important thing. We'll talk about it a lot in unit 3 and 4. Charge sharing. Capacitive crosstalk simply means that this gate, since won't be isolated, there will be a lot of gates. There will be neighboring gates in the chip. Let's say we design a chip, we design a part with dynamic logic. There will be number of gates, number of wires running. Each of those gate nodes and the wires will have some capacitance, and those capacitance will affect the input and the output nodes of a dynamic gate. And since the inputs and outputs are not very noise, they don't have very good noise margin, so they will be affected. Charge sharing, we saw an example of charge sharing. There will be a power supply noise. The power supply is not always fixed VDD. There are some ripples there. There can be feed through noise, means the noise coming from an earlier stage, and there are a lot of noise sources. So summary: domino logic is very attractive for high speed circuits. It is about 1.5 to 2x faster than static CMOS. Why is it faster? Only because inputs and outputs do not see the amount of capacitance as seen by the static CMOS, since we replace the pull-up network by a clocked CMOS. But there are many challenges. We saw monotonicity, we saw leakage, we saw charge sharing, we saw noise margins. Then, since we are talking about speed, domino logic is very fast compared to static CMOS. They are used in very high performance microprocessors, and not for the complete microprocessor design. They might be used for a part of the microprocessor which has to, like for example, ALU. Now, an arithmetic logic unit, let's say the arithmetic part, has adders, has big adders, and now those adders can use domino logic, and the performance of that adder actually determines the performance, determine the performance of a complete CPU, because big adders take a lot of time in evaluation. So we could replace that in some some companies they might be doing, they might be replacing those adders design. They might be converting from CMOS, static CMOS to dynamic logic. I'm not sure. I haven't seen. I personally haven't seen any domino logic design or dynamic gate design, but I've heard it being used in some high speed cases. So summarizing, we saw two logic families, pseudo NMOS and dynamic or domino. Both strive to achieve higher speeds by by getting rid of the pull-up network, since pull-up network or PMOS is the major source of input and output capacity. Pseudo NMOS suffers from a power issue and therefore it is not in use anymore. It suffers because at one time, whenever the output node is zero, both PMOS and NMOS are conducting and there's a big leakage current. Domino logic or dynamic gates try to solve this problem by having a clocked PMOS, but the problem they have is of monotonicity, leakage, charge sharing, and noise. So again, I would like to stress that stress the strength of the static CMOS. So when we go on, we will see libraries, we will see standard cell libraries, and all those circuits, all those standard cell designs are using static CMOS. So we will not see any domino, any dynamic gate, any pseudo NMOS logic. This is more to stress the point that different logic families do exist. They are used for very special circuits where speed of paramount importance, and to appreciate the robustness of static CMOS. It might be slow, it might be big in area, but it is very robust, and that counts for that. That is the major. That is the and it is and one more thing is that we saw in domino we have the clock input. So again, routing clock to thousands or millions of transistors, having an extra input like clock which goes to everything is not easy. The routing resources would be huge, and so the area transfer count will not be increasing, but the wire area, the interconnect area will increase. So it's not an advantage having an extra input as clock. The static CMOS is very robust. It doesn't need a clock except for sequential elements, and the noise margins are very high, and it's reasonably fast. That is why it is more popular. Thank you.